Hello, welcome to today's class. In today's class, we'll talk about number systems, and specifically, we'll talk about binary number systems. So, some of you may already be knowing about binary number systems, but uh, it may, but some of you may not be knowing about it. So, for the benefit of those, I'll be covering. We'll be having this class. So I would like to start with one joke which goes like this. And there are 10 types of people in this world. Those who know binary number systems and those who do not know. So those who already know binary number systems must be understanding uh, what this statement is trying to say. It's actually not 10, it's actually 2. So as I said, most of you already must be knowing binary number systems, and you already know what this statement actually means. I like to start with decimal number systems. So decimal number system is the system we use to count numbers in our day-to-day life. So in this number system, there are 10 digits, 0, 1, 2, 3 up to 9. So there are 10 digits and the base is 10. We'll see what we mean by base is 10, and the value of a digit is determined by its position in the number. Let's take an example, the number 23. Now the number 23 we can represent it as 20 plus 3, and 3 we can write it as 3 into 1, and 20 we can write it as 2 into 10. So now as we can see, 3 has a weight of 1 because it is 3 into 1. So 3 has a weight of 1, and since it is 2 into 10, the digit 2 has a weight of 10. Basically we know that this is ones, this is tens, next comes 100, next comes 1000. So it's the same thing. So here 3 is having the weight of 1 and 2 is having the weight of 10. Now if we try to write the weight of each position, it would go something like this. The first position has a weight of 1, and 1 is nothing but 10 to the power 0. Anything to the power 0 is 1, so 10 to the power 0 is 1. Next is the next position have the weight 10, and 10 we can write it as 10 to the power 1. The next position we know is the 100 place, and 100 we can write it as 10 to the power 2, and after 100 it would be 1000 place. 1000 we can write it as 10 to the power 3, and so on. So the positions have weight as 10 to the power 0, 10 to the power 1, 10 to the power 2, 10 to the power 3, and so on. And as you can see, we are expressing the weights as powers of 10. That's why we say that the base of the decimal number system is 10. If we have a decimal point, then the weights will be something like this. To the left of the decimal point, the weights of the positions will be 10 to the power 0, 10 to the power 1, 10 to the power 2, and so on. And for the positions on the right of the decimal point, the weights will be 10 to the power minus 1, 10 to the power minus 2, 10 to the power minus 3, and so on. Now let us try to express, there is a question which says express the decimal number 568.23 as a sum of the values of each digit. So 568.23, we have a decimal point, and to the left of the decimal point, 8 will have the weight 10 to the power 0. 6 will have the weight 10 to the power 1, and 5 will have the weight 10 to the power 2. Whereas on the right of the decimal point, 2 will have the weight 10 to the power minus 1. It's already mentioned here, the weights. And 3 will have the weight 10 to the power minus 2. So we can express 568.23 as 5 into 10 to the power 2 plus 6 into 10 to the power 1 plus 8 into 10 to the power 0 plus 2 into 10 to the power minus 1 plus 3 into 10 to the power minus 2. And that gives us 5 into 100 plus 6 into 10 plus 8 into 1 plus 2 into 0.1 plus 3 into 0.01. And that gives us 500 plus 60 plus 8 plus 0.2 plus 0.03. So this would be the answer for this question. With that, we go to the binary number system. So what is binary number system? In binary number system, we have only 2 digits. Actually, this would be 2 bits. We have only 2 bits, 0 and 1. And the base is 2. And the value of a bit is determined by its position in the number. So in binary number system, the base is 2. And now if we try to find out the weights of different positions, and if we consider it is a fractional number, so if we have a binary point, on the left of the binary point, the weights will be 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, and so on. And on the right of the decimal point, the weights will be 2 to the power minus 1, 2 to the power minus 2, and so on. And now as you can see, the weights are expressed as powers of 2, and that's why we say its base is 2. The same thing, the weights, I am showing it in a table here. So the weights are 2 to the power 0, then 2 to the power 1, then 2 to the power 2, 2 to the power 3, and so on. And on the right side of the binary point, it is 2 to the power minus 1, 2 to the power minus 2, 2 to the power minus 3, and so on. Now we are converting these powers of 2 to the corresponding decimal number. 2 to the power 0 we know is equal to 1, decimal 1. 2 to the power 1 is equal to decimal 2. 2 to the power 2 is equal to decimal 4. 2 to the power 3 is decimal 8. 2 to the power 4 is 16. 2 to the power 5 is 32. 2 to the power 6 is 64. 2 to the power 7 is 128. And 2 to the power 8 is 256. Similarly, 2 to the power minus 1 is 1 divided by 2 to the power 1, which is 1 divided by 2, so it's 0.5. So 2 to the power minus 1 is 0.5. 2 to the power minus 2 is equal to 1 divided by 2 to the power 2, which is 1 divided by 4. And 1 divided by 4 is 0.25. So 2 to the power minus 2 is 0.25. 2 to the power minus 3 is equal to 1 divided by 2 to the power 3, which is 1 divided by 8, and 1 divided by 8 will be 0.125. So 2 to the power minus 3 is 0.125. Similarly, 2 to the power minus 4 is 0.625, 2 to the power minus 5 is 0.03125, and 2 to the power minus 6 will be 0.015625. Please remember this table. You may need it later for solving some exercises. Now, how do we convert binary numbers to decimal? So here is one question. Convert the binary number 1101101 to decimal. To do this conversion from binary to decimal, we'll first write down the weights of each bit position. And as we know already, the weights of each bit position is 2 to the power 0, then 2 to the power 1, 2 to the power 2, and so on. Next, we write down the given number. The given number is 1101101. So I write it down 1101101. And now to calculate the decimal number, the decimal number will be 1 into 2 to the power 0 is 0. Sorry, 1 into 2 to the power 0 will be 2 to the power 0. 0 into 2 to the power 1 will be 0, and that's why we don't see 2 to the power 1 here. 1 into 2 to the power 2 will be equal to 2 to the power 2. 1 into 2 to the power 3 will be equal to 2 to the power 3. 0 into 2 to the power 4 will be 0, and that's why we don't see 2 to the power 4 in this expression. 1 into 2 to the power 5 will be 2 to the power 5, and 1 into 2 to the power 6 will be 2 to the power 6. And hence the given number 1101101 can be written as 2 to the power 6 plus 2 to the power 5 plus 2 to the power 3 plus 2 to the power 2 plus 2 to the power 0, which is 64 plus 32 plus 8 plus 4 plus 1, which is 101. Now next question is to convert a fractional binary number 0.1011 to decimal. We would use the same method. We'll write down the weights first. For the positions on the right of the binary point, we know that the weights are 2 to the power minus 1, 2 to the power minus 2, 2 to the power minus 3, 2 to the power minus 4. Now the given number is 0.1011, 0.1011, and hence now I can write the given number as 1 into 2 to the power minus 4 plus 1 into 2 to the power minus 3. 0 into 2 to the power minus 2 is 0. That's why we don't see 2 to the power minus 2 here. And 1 into 2 to the power minus 1 is 2 to the power minus 1. And now from the previous table, if you remember the previous table here, 2 to the power minus 1 is 0.5, 2 to the power minus 3 is 0.125, and 2 to the power minus 4 is 0.625. And hence I can write 0.5 plus 0.125 plus 0.0625, which gives us the decimal number 0.6875. So binary 0.1011 is equal to decimal 0.6875. Now how do we count in binary? And let's say we have only one bit, and we know that the bit will have the weight 2 to the power 0, which is equal to decimal 1. Now when we have only one bit, that bit can be either 0 or it can be, or else it can be 1. These are the only two values we can put in that bit position, because we have only 2 bits in the binary number system. Now when we put 0, the corresponding decimal number will be 0 into 1, which will be equal to 0. If I put 1, then 1 into 1 will give us the decimal number 1. So decimal number 0 will be represented as 0 in binary, and decimal number 1 will be represented as 1 in binary. Next, if we want to represent 2, it's not possible to represent 2 using only one bit, because using one bit we can represent only these two numbers. Now to be able to represent 2, we have to add one more bit. So now we have 2 bits, and the weights will be 2 to the power 0 and 2 to the power 1. In decimal, the weights of those bit position will be 2 to the power 0 is 1 and 2 to the power 1 is 2. So the weights will be 1 and 2. Now if we have to represent 2 can be represented as 1, 0, because 1 into 2 is 2 plus 0 into 1 is 0, so 2 plus 0 will give us 2. So we see the decimal 2 is represented as 1 0 in binary number system, and once you understand that, you will also understand the joke we had at the very first slide. So 1 0 in binary means decimal 2. Now to represent 3, it will be represented as 1 1, because 1 into 2 will give us 2, plus 1 into 1 is 1, so 2 plus 1 will give us 3. So these are the 4 numbers we can represent using only 2 bits. If I have to represent 4, it's not possible to represent 4 using only 2 bits, because these are the only 4 numbers we can represent using 2 bits, because these are the only 4 combinations we can have: 0 0, 0 1, 1 0 or 1 1. No further combinations are possible using only 2 bits when we have only 2 bit positions. So now to represent 4, we have to add one more bit. So when we add one more bit, we'll have now 3 bits, and the weights will be 2 to the power 0, 2 to the power 1, 2 to the power 2, which in decimal will be 1 2 4. And once we have added one more bit, now 4 can be represented as 1 0 0, because 1 into 4 is 4, and 0 into 2 will give us 0, 0 into 1 will give us 0, so it will be 4 plus 0 plus 0, which gives us 4. So decimal 4 will be represented as binary 1 0 0. Now if we want to represent 5, it will be 4 plus 1. 4 plus 1 is equal to 5, so I can write 1 0 1. If we have to represent 6, it will be 4 plus 2, so it will be 1 1 0. If we have to represent 7, it is 4 plus 2 plus 1. 4 plus 2 is 6, plus 1 is 7, so all the bits will be 1 1 1. And these are the only 8 numbers that can be represented using 3 bits. So if we have to represent 8, 8 cannot be represented using only 3 bits. So we have to add one more bit position, and as we add one more bit position, the weights of each position will now be 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, which in decimal is 1, 2, 4 and 8. So now 8 can be represented as 1 0 0 0. So 8 will be represented as 1 0 0 0. And if you have to represent 9, 9 is 8 plus 1. Since 9 is 8 plus 1, so it will, in this position it will be 1, and in this position it will be 1. The other two position will be 0. So 9 will be represented as 1 0 0 1. So 8 plus 1 is equal to 9. The other two bits we don't need, so they will be 0 0. So like this we can keep on representing, and we'll see that using 4 bits we can represent up to 15. And please remember this table also. So 0 using 4 bits is represented as 0 0 0 0, 1 is represented as 0 0 0 1, 2 is represented as 0 0 1 0, 3 is represented as 0 0 1 1, 4 is represented as 0 1 0 0, 5 is represented as 0 1 0 1, 6 is represented as 0 1 1 0, 7 is represented as 0 1 1 1, 8 is represented as 1 0 0 0, 9 is represented as 1 0 0 1, 10 is represented as 1 0 1 0, 11 is represented as 1 0 1 1, 12 is represented as 1 1 0 0, 13 is represented as 1 1 0 1, 14 is represented as 1 1 1 0, and 15 is represented as 1 1 1 1. So please remember this table, and if you try to understand how to create this table, you can use the previous method I said, or If you look at how the counting proceeds, we first have all the bits 0 0 0 0, and then for every next number we keep on toggling this first bit. So it is 0 1, then again 0 1, then 0 1, then 0 1 0 1. So this bit gets toggled for every time, and here in the next position the bits get toggled every 2 times. So it is 0 0, then 1 1, then 0 0, then 1 1, 0 0, then 1 1, 0 0, then 1 1. Whereas the next bit position toggles every 4 times. So for 4 times it is 0, then 4 times it is 1, the next 4 times it is 0, and the next 4 times it is 1, and the next position it will toggle every 8 times. So 8 times it is 0, and the next 8 times it is 1. And you can try to understand it also like this. When we toggle from 0 to 1, the previous bits do not change, they remain as it is. So if it is 0 0 0, they remain as 0 0 0. But when we toggle from 1 to 0, this bit, when we toggle from 1 to 0, we toggle previous bits also till we reach a 0. So when you toggle from 1 to 0, I go back and change the previous bit also. So previous bit is 0, we change it to 1, and since this is 0, we stop here itself, we don't go to the next bits. If it is a 0, we stop. So this 1 changes to 0, and this 0 changes to 1. That's 2, 0 0 1 0. Next we change from 0 to 1. When we change from 0 to 1, we will not change the previous. So it was 0 0 1, it will remain as 0 0 1. However, when we change again from 1 to 0, remember when we change from 1 to 0, we'll change the previous bits. So we change from 1 to 0, I'll go to the previous bit, we'll change 1, since it is 1, we'll change it to 0. And since we have not reached the 0, I'll go to the next previous bit also, and this 0 is changed to 1. And since we have reached 0, we'll stop here itself, I'll not go to the previous bit. So 0 0 1 1 will change to 0, this gets changed to 1, this gets changed to 0, and this gets changed to 0. Next we toggle from 0 to 1. When we toggle from 0 to 1, the previous bits do not change, they remain as it is. So it was 0 1 0, it will remain as 0 1 0. And again when we change from 1 to 0, when we change from 1 to 0, we have to change the previous bits. So I go back here, I change from 0 to 1, and since this bit itself is 0, I don't go to the previous bit. As soon as we get a 0, we'll stop there itself. So here I get a 0, so I stop here. So this 1 remains as 1, whereas this 0, it changes to 1. And then again we change from 0 to 1. When we change from 0 to 1, we don't change the previous bits. It was 0 1 1, it remains as 0 1 1. But when I change from 1 to 0, I'll go back and change the previous bits. So the previous bit was 1, it changes to 0. Since I have not reached the 0, I'll go back to the previous bit, and this 1 is again changed to 0. We still have not reached the 0, so I go back to the previous bit, and this time I get a 0. So I change the 0 to 1, and I'll stop here itself. So this 0 is changed to 1, this 1 is changed to 0, this 1 is changed to 0, and this 1 is changed to 0. And so this is another way to look at how to count using binary. So with that, I'd like to stop today's class. In next class we will talk about converting decimal numbers to binary. With this, I'd like to end my class today. Okay, thank you, bye.